Okay, we've got a short answer here for photoelectron spectroscopy. We've got a photoelectron spectrum for an unknown element, and now we've got some questions we want to answer. So first, we want to draw an X above the peak that corresponds to the orbital with electrons that are, on average, closest to the nucleus. And we want to justify in terms of Coulomb's law. So what is Coulomb's law? Coulomb's law is like this. We've got the two charges up top, and we've got r squared on the bottom. And so all this is saying is that as the radius or distance between them increases, the denominator gets bigger, the fraction gets smaller, and the force gets smaller. So the electrostatic attraction, we're talking about this being greater the closer they are together. So the closest to the nucleus will have the greatest binding energy. And so we can see binding energy right here. It's biggest to the left. So it starts very big and then gets very small. And so the closest to the nucleus, it's going to have the largest binding energy. So it's the leftmost peak. So we're going to put an X right there. Okay, so closest to the nucleus, we know that has the largest binding energy, so leftmost peak. Now, based on the spectrum, write the complete electron configuration of the element. And so when we're reading these, remember, all we need to understand is that we're basically just doing Aufbau principle from left to right. Each of these peaks represents a subshell, and these are the subshells in increasing energy. So we're going from the 1s subshell to the 2s, to the 2p, to the 3s, to the 3p, etc. And so as long as we know Aufbau, we know what these subshells are, right? We're just following Aufbau from left to right. So these are the two 1s electrons, so 1s2. This right here is 2s2. This is going to be 2p6. And then we got this last one here, this is 3s1. This must be 1 because what we're understanding is this has to be 1s2. This has to be the two 1s electrons. So these lines, they're not telling us the number, relative number of electrons, relative number. But we know that that's 2 electrons. So let's mark that. Let's say 2, 4, 6. Each line is 2 electrons. Okay, so first of all, we just got this. It's 1s2, 2s2, 2p6, 3s1, right? That must be the electron configuration. We've got 2 in the 1s, 2 in the 2s, 6 in the 2p, and 1 in the 3s. That's how we're going to read these. And then lastly, on the graph, draw the peak corresponding to the valence electrons of the element that has one more proton in its nucleus than the unknown element has. Right, so if we've got one more proton, we've also got one more electron. So this one is 3s2. So first of all, if it's 3s2, it's going to be taller. So we're over here. Let's change colors. We're going to be over here, but instead of the peak stopping halfway, we're going to go all the way to this line because it's 3s2. But we also need to understand that if there's one additional proton in the nucleus, the binding energies are going to be slightly greater. And if the binding energies are slightly greater, the peak is going to shift to the left a little bit. So we would probably want to put this about here. Right here is here would be this peak for C. It is just slightly to the left of this first peak, and it goes all the way to 2 because it's 3s2. One additional proton, one additional electron for the neutral atom. So that was a short answer. This is just going over some basic principles we should recall about photoelectron spectroscopy.